Now that we have an understanding of the 7-layer OSI model, we want to take a look at the 4-layer TCP/IP model. The OSI model, it was developed to be a fairly generic and flexible model, but most of the traffic we deal with today, it's IP-based. So this TCP/IP centric model, it might be a better fit for us. And this TCP/IP model, it's also known as the TCP/IP stack, or the Department of Defense, or DoD model, because it was originally developed by the United States Department of Defense. And at the bottom, we have the network interface layer. Then we have the internet, the transport, the application layers. And what we're going to do over the next few videos is to show you how these layers map to the 7 layers in the OSI model. But to get started, let's take a look at the network interface layer. At the bottom of the TCP/IP stack, we have the network interface layer. And the network interface layer, it corresponds to, it maps to the 2 bottom layers of the OSI model, specifically the physical layer and the data link layer. Some literature that you might read might refer to the network interface layer as the network access layer. So those terms are synonymous. And if we think about the network interface layer, there's nothing particularly unique about the network interface layer in the TCP/IP stack versus the network interface layer in the OSI model. After all, the TCP/IP stack, it's concerned with the suite of protocols that fall under the TCP/IP umbrella. And IP traffic at the network layer of the OSI model, it can travel over a variety of layer 2 transports. It can travel over frame relay, it can travel over ATM, it can travel over the point-to-point protocol. We can have a variety of physical media over which it travels. It could go over fiber optics, unshielded twisted pair. We could be using a wireless network. The point is, there's nothing terribly TCP/IP specific about the network interface layer. The same things we learned about the physical and the data link layer under the OSI model, they apply here at the network interface layer of the TCP/IP stack. The internet layer of the TCP/IP stack, it maps to the network layer of the OSI model. And if we think about the OSI model at the network layer, we might have several protocols here. We can have routable protocols such as IP, IPX, AppleTalk. We don't see that much these days, but those are routable protocols. But in the TCP/IP stack, we're focused on IP, so that's the main component at the internet layer. And to understand IP a bit better, let's take a look at the format of an IP version 4 packet, and let's highlight a few of the fields. For example, notice that we have a source and a destination address. We have source and destination IP version 4 addresses specifically. The protocol field, that identifies the transport layer protocol, the layer above this, it identifies the transport layer protocol to which we need to send this packet. Also check out the TTL field, that's the time to live field. This field has a certain value and it gets decremented, it gets reduced by 1 every time that this packet with this IP header gets passed from one network to another. Every time it gets routed, every router hop, we decrement that time to live value. Let's say that we had a time to live value of 120. That packet goes through a router and the time to live value is going to be decremented down to 119. A big advantage of this that we do not have with switches, by the way, is that if we have a loop, some sort of a routing loop where a packet just starts to circulate and circulate throughout the network, it's not going to circulate indefinitely. Once that time to live value is decremented to a 0, it's going to be dropped. However, a frame down at the data link layer of the OSI model or the network interface layer of the TCP/IP stack, that frame does not have a time to live value, and a frame could circulate indefinitely in a switched topology. And there's a fix for that, and we'll be talking about that later. But for now, understand that this time to live field is going to prevent an IP packet from endlessly circulating through the network. The transport layer of the TCP/IP stack should be easy to remember because it maps to the same name, the transport layer of the OSI model. And the 2 primary protocols found at the transport layer in the TCP/IP stack are TCP, Transmission Control Protocol, and UDP, the User Datagram Protocol. First, let's examine the header of a TCP segment. Notice that we have source and destination ports. These ports, they identify to which upper layer protocol data should be forwarded, and from which upper layer protocol data is being received. The window size says how many bytes can a receiver receive before they expect an acknowledgement. This is a way to do flow control. Remember what flow control is? Flow control is a way for the sender to be told to slow down because it's transmitting too aggressively. You see, the sender can start out with a small window size, let's say 1 segment. And if that segment is delivered successfully, as evidenced by an acknowledgement that we receive, we can double the window size. We can go to 2 segments, and if that is successful, we can double again and go to 4, 8, 16, 32, 64, 128, 256, 512, 1024, and so on and so on. In fact, the current standard allows us to have over 2 billion bytes that we can send before we expect or require an acknowledgement. But the window size can grow over time. If we get to a point where we are sending too aggressively and a packet does get dropped, the receiver, when it sends an acknowledgement, it can say, I acknowledge that I received this segment and this segment, and I want this next segment, and then the sender could see that, whoa, I've already sent that segment. It must have been dropped. I must be sending too aggressively. That can cause the sender to reduce its window size. That's something called TCP slow start. We also see that we have a sequence number field. This allows segments to be put back in the correct order if they arrive out of order. There is an acknowledgement number. The acknowledgement number indicates the next sequence number that the receiver expects to receive. And this is a way that the receiver lets the sender know that all the segments up to that sequence number have been successfully received. In addition to TCP, we said the other big player at the transport layer was UDP, the User Datagram Protocol. And the first thing we're probably going to notice here is it's much smaller. It has a lower overhead. That's one of the big benefits of UDP. TCP, it's considered a connection-oriented protocol, or in other words, it's a reliable protocol. If we send segments, we get acknowledged that those segments were successfully received. And if they were not, we can send them again. So it's a reliable transport mechanism. UDP, not so much. With UDP, we don't have a sequence number. We don't have a window size. We don't have an acknowledgement number. This is a connectionless protocol. There is no acknowledgement. Therefore, it is referred to as an unreliable protocol. And I know that might sound bad, but there are certain applications where this is actually a good thing. For example, if you're sending streaming audio or streaming video, you probably don't want to introduce the delay of when you have to wait for an acknowledgement. And if a packet gets dropped, to have to retransmit, that could lead to excessive delay in an audio or video stream. If we send audio or video using UDP, for one thing, we don't have to worry about the big overhead. We have a much smaller header size. We have a more efficient use of bandwidth. And we really don't care if we're not told about a dropped segment, because honestly, we don't want to retransmit it anyway. If we waited for that acknowledgement, it would introduce significant delay into the transmission. And I've experienced this. I used a streaming audio program that was designed to use TCP as the transport, and it was where multiple participants could participate in this audio conversation. And we noticed that after we had been in a conversation for some time, and based on network conditions, a few packets had been dropped, there was a delay in our transmissions. It started to not be real time. We started to talk on top of each other. It was not a good thing, and that's because TCP was being used. We were waiting for acknowledgments, we were retransmitting drop packets. That's not good. That introduces delay. So UDP, it's actually a great solution for something like streaming audio or streaming video. We don't have many fields. We do have source and destination ports, much like the TCP header did. There is an optional UDP checksum, which can detect errors, and the other field is a length field, which says in bytes, how big is this UDP segment? I would say that one of the biggest differences that we have between the TCP/IP stack and the OSI model is up at the application layer of the TCP/IP stack. You see that this one TCP/IP stack layer, it encompasses 3 OSI model layers. It encompasses layer 5, the session layer, layer 6, the presentation layer, and layer 7, the application layer. And I would consider this to be a very good thing. This reduced complexity can make it a lot easier for network designers, network administrators to classify certain protocols or certain network technologies. For example, let's take the protocol of H.225. that could be used to set up an audio or a video stream. And unless you understand the inner workings of H.225, it might not be super clear where it fits into the OSI model. It kind of seems like it might be the session layer, but could part of it be the presentation layer? You really would have to know the protocol quite a bit to be able to properly classify it. However, with the TCP/IP stack, we can quickly recognize that this belongs at the application layer because it's a higher layer protocol. It gets encapsulated inside of TCP, so no problem. We'll just categorize it at the application layer.